Hello students. Okay, today we are going to learn about how to find volume of a solid using the shell method. So here I have a solid, okay, and what it has is cylindrical shells wrapped around. So it's made up of lots of cylinders, hollow cylinders that are nested in with each other to create this solid. So now, if you look at this, you can see that it is rotated about this axis right here. Now, if I were to put this solid laying here and make that toothpick the x-axis, then each of my shells are rotating about the x-axis. If I were to put it this way, then it would be rotating about the y-axis. So first, let's figure out how we find the volume of one of these shells. So you can see that the volume of this solid, it's got 1, 2, 3, 4 shells in it, each cylinders. So the volume is going to be equal to volume of the first shell, the second shell, the third shell, and then the fourth shell. And so what is one shell? Shell number 1, the volume of the cylindrical shell number 1. So what we're going to do is we're going to take out one of these, like so. And then you can see that the shell is actually like a rectangle. And so this would be a very long rectangular prism. So if I were to find the volume of this very long rectangular prism, how would I do that? So then the volume would be equal to the area of the base. So I have this right here, which matches up with this, which, if you recall, went around this cylinder. So you can see that the base is equal to 2 pi r. It's equal to the circumference of this cylinder. Okay, where r would be the radius that extended from the axis of rotation to the center of this shell. And then the height would just be the height of that figure. So then the volume would be 2 pi radius of whichever volume or whichever cylindrical shell you're on. So I'm just going to say n times h, n, because each one of these cylinders have a different radius. And each one of these cylinders also have a different height. So this is going to vary depending on which shell you're on. And then we take the area of this base and we multiply it by your delta. So it could be delta x or delta y. And that would give us the volume of this figure. So now let's figure out how we would determine if we're going to have it in terms of x or in terms of y. So if you look, if I have it rotated about the x-axis, and then if I create a y-axis like so, then when you look at this, you can see that each of those shells, the thickness of each one of those shells is measured off of the y-axis. So if it is rotated about the x-axis or rotated about a horizontal line, then the thickness of each shell is going to be measured off of the y-axis. So if it's about a horizontal line, then it's going to be in terms of y. And if it's about a vertical line, so let's see, if I have it about this vertical line, Then this right here becomes my x-axis, and you can see that the thickness of each shell is going to be measured off of the x-axis. So the volume formula that we have would be volume is equal to the integral from A to B of your area of your base. So I'm going to say 2 pi r, which is going to vary, and h, which is going to vary. And so this is the area of the base times your delta. Delta x or delta y. So if it's rotated about a horizontal line, the volume is going to be, I'll factor out the 2 pi, from y equal to A, y equal to B, r of y times h of y, because the radius and the height are going to be functions depending on what your y value is, dy. And if it's a vertical line, then the volume is going to be 2 pi, the integral from x equal to A, x equal to B. So you can see like this. It's rotated about a vertical line, but each of your shells are, the thickness of your shells measured off of the x-axis. And it's going to be r of x times h of x dx. So during the video, you can pause anytime you want so that you can copy everything down or glue anything in. So now, this is what we get from the Larson book. And I'm just going to change the notation a bit. Here they have the exact same formula around a horizontal axis. Here you have the shaded region that you want to rotate. And so when you rotate this part, this becomes your cylindrical shell. And I'm going to change this P to an R. So represents radius. And the radius is this length right here, the distance from the axis of rotation to the cylindrical shell. And here, if you rotate about a vertical line, then this is measured off of the x-axis. And now your radius is the distance from this vertical line to the center of your cylindrical shell. So I'm going to call that R, and I'm going to call this R, and I'm going to call this R. The height of your cylindrical shell is now the length of this line segment, the length of this line segment that lies in your shaded region. So the radius is always the distance from the axis of rotation to your cylindrical shell. The height is the length of the segment in your shaded region. Okay, so we're going to do our first example.